Hello everyone. Tonight we shall be covering our 11th lesson of thermodynamics, which is the diesel cycle. So here I have a diesel cycle drawn for you on a PV or pressure volume diagram. Let's start out by labeling the processes. So 1 to 2, what's that gonna decrease the thickness of that, is an adiabatic compression. 2 to 3 is isobaric expansion. 3 to 4 is adiabatic expansion. And 4 to 1 is the part where you're doing the heat rejection of the cycle. So, as you can see here, this is a diesel cycle is a closed system because you're dealing with an engine. This is all done within it is a piston chamber setup. So you're operating within a closed system. So that means for our first law, we are using the delta U is equal to Q minus W. So let's break down the system. 1 to 2. Remember, 1 to 2 is adiabatic compression, so Q is equal to 0. Then you have delta U 1, 2 is equal to negative work. So you have the mass in the system times U2 minus U1 is equal to negative work. The work for the compression cycle is equal to, or the compression part of the cycle is M times U1 minus U2. So now let's do 2 to 3. So delta U is equal to Q, or delta U23 is equal to Q23 minus work 23. Now, how do we find the pressure, or not the pressure, the work of the system? Well, if you recall, work is equal to work over mass is equal to the integral of pressure times the change in volume. Well, isobaric pressure is constant, doesn't change with respect to volume. Therefore, your work equation becomes P delta V. So then plug this into your first law equation. You get U3 minus U2 is equal to Q23 minus P times, forgot to divide this by mass, times V3 minus V2. Okay, well then this becomes U3 plus P V3 minus U2 plus P V2 is equal to Q23 over M. And if you recall, enthalpy is equal to the internal energy plus the pressure times the volume. So this becomes enthalpy at state 3 minus enthalpy at state 2 is equal to the heat input of the cycle. All right, so now let's do the next part, 3 to 4. 3 to 4. This is adiabatic expansion. So Q34 is equal to 0. So like before, work is equal to the mass times U3 minus U4. All right, so 4 to 1. It's isochloric, right? Did I make sure I wrote that up there? Yeah, I did not actually. 4 to 1 is isochloric. So since that's isochloric, if work is equal to the integral of the pressure with respect to the change in volume, if there's no change in volume, work is 0. So then it becomes M times U4 minus U1 is equal to Q41. So these are the first law statements for each step in the diesel cycle. Pretty standard with how we've done, and just remember every thing we do in thermodynamics is going to be in some way related to the first law or the second law. So if there's one takeaway you need to get from thermodynamics is you really need to have a deep understanding of those laws of thermodynamics. Because if you know those, you can, not exaggerating here, you can analyze basically every single cycle you will uncover, both in classes and in life. So now if you recall from the Otto cycle, there was another thing, they had a compression ratio. Well, so does here. This also has a compression ratio. I'll label that in red now that we're done analyzing the physics behind this thing. So compression, well, we're not done, but we're done writing out the first law. So again, it has a standard compression ratio of R equals V1 over V2, which is equal to VR1 over VR2. If you recall from when you're dealing with ideal gases such as air. However, this does have a compression ratio, but diesel has something different. Recall here, you're having a change in pressure. I'm not having a change in pressure. This pressure from 2 to 3 is constant. However, you're having a change in volume. Well, you need to know what that change in volume is. So, diesel engines have another constant called a cutoff ratio, or RC. So what the cutoff ratio is, it's between the end and start of the combustion. Oh, that's terribly written. That is not even legible. I'm sorry. So the compression ratio is the ratio between the end volume and the start volume for the combustion phase. And the combustion phase happens during phase 2-3. Because how a diesel engine works is air is injected, gas is injected, and instead of having an igniter like a Otto cycle engine might, diesel, what it does is it puts so much pressure on the gases that it creates a spark. So diesel engines do not actually have a spark plug in it that combusts the gases. The pressure that the piston puts on the gases actually causes that combustion. So RC is equal to V3 over V2, because remember 2 to 3 is the isobaric part of the process, and it's where the gases are ignited by the pressure caused by the piston. Okay, so when would you use these? Well, you still have these standard from, if you recall from the Otto cycle, we use the compression ratios to find the different temperatures and volumes at each point. Well, same thing goes here. For processes 1 to 2, T2 over T1 is equal to V1 over V2, K minus 1, same as the Otto cycle. And of course, we can rewrite that as T2 over T1 is equal to R to the K minus 1. And again, you're going to do that for all the others except during phases 3 to 4. This is where it changes, the adiabatic expansion. Well, you have T4 over T3 is equal to V3 over V4 to the K minus 1. Alright, same as you'd expect up there. However, you don't know what V3 is, but you know what V4 is. But you might not know what T4 or any of these constants are. You might not. But whenever you're dealing with a diesel cycle, you will always know what RC is, and you'll always know what R is. So we transform them. This becomes V3 over V2 divided by V4 over V2. Basically just divide top and bottom by V2 to the K minus 1. And if you recall, V4 is equal to V1. Well, V1 over V2 is R, and up here, V3 over V2 is the cutoff ratio. This becomes RC over R times, or 2 the K minus 1. So that's how you find the temperature ratios for the adiabatic expansion part of the cycle. So Oh, another thing. You might have also noticed that unlike the Otto cycle, the diesel cycle has two stages where work is being performed. It's being performed in the 2 to 3 stage and the 3 to 4 stage. So now we're not simply having it's like, okay, compression, heating, workout, cooling. It's now compression, heating and getting workout, more workout, and then cooling. So now we have to take into that extra work into account when we're analyzing the efficiency of this engine. Now, when you're dealing with diesel cycles, as with Otto cycles, you're also dealing with cold air standard. Now, when you're dealing with cold air standard, you also have specific efficiency equation which you can use called, or which is written as n times 1 minus 1 over r to the k minus 1 times rc to the k minus 1 all over k times rc minus 1, where k is the ratios of specific heats for air, which is 1.4. Now, again, this equation is only when you're dealing with a cold air standard. If you want to find the efficiency of an engine when you're just doing it normal, not cold air, or you're not told it's cold air standard, or you're not working with that assumption, again, work of the cycle over the Q in. That'll even work here. This is just not an easier way, but you don't have to do as much work because you will to find the efficiency of an engine, because you will be given the compression ratio, you'll be given the volume ratio or the cutoff ratio, and you will know the K value for air. All right, so I'll be right back. I will have a problem for us to walk through to show you how to analyze a diesel cycle. Hello everyone, we are back. So here's the example problem we are going to deal with. We are told that the compression ratio of our cycle is 18. At the beginning of the cycle, our temperature is 300 Kelvin and our pressure is 0.1 megapascals. And we're told that it has a cutoff ratio of 2, and we're told it's air standard. Since it's air standard, we can use this efficiency equation if we need to. Well, we are told to, because we need to find the thermal efficiency in part B. So in this problem, you're going to find the temperature and pressure for each state of the process. I forgot to write state, sorry. Each state of the process. We are going to determine the thermal efficiency of the cycle, and we're going to determine the mean effective pressure of the cycle. So first things first is we got to find the values at the states. So state point 1, we are told temperature is 300 Kelvin. Let's switch to black. Pressure of 1 is equal to, 0.1 megapascals. And if you recall from the Otto cycle problem, we used a table to get the values for the air. We are using the Moron-Shapiro Fundamental Thermo Textbook 8th edition, and we're using table A22. So A22 from the Moran-Shapiro Fundamental or Thermodynamics. Okay, it doesn't really matter. Either way, we are using a table from the Moran-Shapiro Fundamental Thermodynamics book, 8th edition. This table, doesn't matter what the edition, is the same for any table, or any engineering table. So you can look up air table, but honestly, when solving these problems, oftentimes you just have to interpolate, and it's really kind of not necessary to explain how to do the problem. So I'm going to just provide you with the values so that you can understand the process of how to solve the system, instead of us wasting time and like, okay, this is the chart, I have to go get this point and I need to now interpolate it. So here's the values. So at state point 1, P1 is 0.1 megapascals. U1 is, or the internal energy at state point 1, is 214 kilojoules per kilogram. VR1 is equal to 621.2. All right. So, since 2 to 1 is isentropic, and we need to find the values at state point 1, V we know that VR2 over VR1 is equal to V2 over V1, and we know that V2 over V1 is 18 because we are told the compression ratio, which is written wrong here. No, it's not written wrong here. I'm sorry. Compression ratio. V2 over V1 is 1 over 18. So this becomes VR2 over VR1 is equal to 1 over 18. Sorry. So VR2 is equal to VR1 over 18, which is equal to 34.51. So we go to the table for look in the VR column for 34.51. You'll see that's not really there, but it's close to some values. You interpolate, and you get that T2 is equal to 898.3 Kelvin, and H2 is equal to 930.98 kilojoules per kilogram. Now remember, we have to find the pressure too. Well, this is an ideal gas, so we can use just the ideal gas equation, PV equals nRT. Now, nR is going to be constant throughout the entire thing, so we get P2 V2 over T2 is equal to P1 V1 over T1. So we can do P2 is equal to P1 V1 over T2 over V2 T1. V1 over V2 is 18, so this becomes 0.1 times 18 times 898 over 300. P2 is equal to 5.39 megapascals. All right, so that's state point 2. All right, let's find state point 3. Okay, so since, well, we know P3, because P3 is equal to P2, which is equal to 5.39 megapascals, so that was easy. And we can just simply use the ideal gas equation again, and we get that T3 over V3 is equal to T2 over V2. So you get that T3 is equal to V2 over V3 times T2. Well, V2 over V3 is the, I'm sorry, I think I messed that up. I think I messed this up. One moment. T3 over V3 is equal to T2 over V2. I mislabeled it or something. So then T3 is equal to V3 over V2, T2. There we go. So V3 over V2, as I told you earlier, is the compression ratio for the diesel cycle, which we are told is 2. So this becomes 2 times T2, which is 2 times 898, which is equal to 796 Kelvin. Now we know the pressure and temperature at state point 3. Since we know the pressure and temperature at state point 3, and we're going to need it for later on, we are going to write that H3 is equal to 1999.1 kilojoules per kilogram, and VR3 is equal to 3.97. All right, let's do this. Oh, I never wrote down these values for state point 2. So where is that? Okay, H2 is equal to 930.98 kilojoules per kilogram. Now, you might be wondering, well, John, why are you writing the internal energies? Why are you writing the enthalpy values for these? We're looking for the state point temperature and pressure, and we're looking for the thermal efficiency, right? We don't need that because we have these equations, and they're not needed to find the temperature and pressure. You're right, they're not. But the mean effective pressure equation requires us to know the work done by the cycle. So we need to know the work done by each part of the cycle, and we need to know the heat input at certain portions of the cycle, which we'll get to later when we're going over mean effective pressure. But we need those values for later, so we're just calculating them now. State point 4. Okay, so we know that VR4 over VR3 is equal to V4 over V3. So this is equal to, or VR4 is equal to VR3 times V4 over V3, which is equal to V4 over V2, V2 over V3, VR3. This becomes R over RC times VR3, which becomes 9 times VR3. Therefore, VR4 is equal to 35.73. Go to the table, interpolate, you get that T4 is about 887.7 Kelvin. U4 is about 664.3 kilojoules per kilogram. And so now we need to find the pressure at state point 4, because now we know the temperature. Well, the pressure, state point 4, we would just simply use the ideal gas equation from state point 4 to state point 1. Well, state point 4 and 1 is isochloric. Therefore, their volumes are the same. So you get P4 over T4 is equal to P1 over T1. So P4 is equal to P1 times T1 over T4, which is equal to 0.1 times 887 by 300, which is equal to 0.3 megapascals. There we go. So then, as you can see, by using the volume ratio equations and the ideal gas equation, we found the temperature and pressure for each individual state. And then from that, we also found by using the ideal air table, we are able to find the enthalpies and internal energies and volume ratio, reduced volume ratios for each individual point. And we can use that to solve our problems. All right, good work, team. Now we're going to find part B, which is calculate the Calc the thermal efficiency. So remember, this was air standard. So we can use this equation up here. Oh, this was air standard. That's cold air standard. Guess we can't. Never mind. So I have to do this the hard way. Efficiency is equal to the work over the cycle over the total heat added. Well, what's the work of the cycle and what's the heat added? Well, that's going to be the pressure of 2 times the change in volume of 2,3 plus the work done by 3,4 minus the work done by 2,1 all over Q23, which is equal to, what's the pressure at state point 3 again? 5.39. 539 kilojoules, or kilopascals, because I have to convert to kilopascals, times the volumes, which I do not know. So that means this is going to get a little bit more complicated. Well, I can find it. I can find it because I know that I can find V2 and V1. So but we're going to do that. So we're going to do N is equal to the Q in minus Q out over Q23, which is equal to, or Q in, which is equal to Q23 minus Q41 over Q23, which is equal to 1 minus Q41 over Q23. Now I can find Q1, Q41 really easily because since it's isochloric, no work's done. So it's just simply going to be equal to 1 minus U4 minus U1 over, again, the heat input of Q23 up here, somewhere here, is the change in enthalpies of the two. So H3 minus H2. If I plug in my numbers, I can find the thermal efficiency equation. But back up here to this original efficiency equation here. Now you might be saying, John, well, we don't know the volumes at 2 and 3. Well, you can find them because we are told, can we find them? We cannot find them, actually. Yeah, we're not given the amount of material in there, we're not given the volume of it, so yeah, we actually can't find them. So we cannot use this work equation. It's not an option because there's no way to find the volumes. As a result, we have to refer to our original equation where all the heat that goes in has to go out in some, or all the energy that goes in has to go out in some way. So the energy in minus the energy that is ejected has to be the work. So we use this bottom equation to find the thermal efficiency. That was my fault for bringing up no, because it was able to explain why we can't use the first equation and have to resort to the alternative method. So back to that equation, let's plug in our numbers. Well, so efficiency is equal to 1 minus 664.3 minus 214.07 all over 1999 minus 930.98. This gets 0.578, which is 57.8% efficient. Now the last one, which is the mean effective pressure. Well, if you recall, the mean effective pressure is equal to work of the cycle divided by the mass all over V1 minus V2. Well, this is written as work of cycle over M. Take out V1 and you get 1 minus 1 over R. Alright, well, work of the cycle is the top part up there. So, well, it's actually not this because it's 1 minus that. So, work of the cycle over M is equal to all the heat that has to come in minus all the heat that has to go out, which is equal to H3 minus H2 minus U4 minus U1. Plug in those values, you will get 617 kilojoules per kilogram. Now we have to determine, actually, the specific volume at state point 1. So we now have to find that volume. So ideal gas equation. P1 V1 is equal to R M T1. Well, what's R and M? Well, R and M is the not specific volume. R is the universal gas constant, and M is the molar mass of air. So V1 is equal to 831.4 Newton meters over 28.97 kilograms times, no kilogram, yeah, that's just all units, break it down, times 300 Kelvin, tap divided by pressure, divided by, it was, what was the pressure? 0.1 megapascals. So mega, that'd be 0.1 times 10 to the 6th, which is 10 to the 5th Newton per meter squared. This all comes out to 0.861 meters cubed per kilogram. Plug all those in. 617 kilojoules per kilogram over 0.861 meters cubed per kilogram. And wait, I missed a value. What did I miss? Oh, right. Times 1 minus 1 over 18. That would have been bad. Then, as you can see, these are all different units. So you have to add in some dimensional analysis. So you're going to do 10 third newtons meters per 1 kilojoule. So we can convert kilojoules to meters. And then we need to convert back to megapascals because it wants it in megapascals. 6 newtons per meter squared. This all comes out to 0.76 megapascals for the mean effective pressure. Don't worry, I'm about to summarize this entire problem. So, what did we do first when analyzing a diesel cycle? First things first is we read the problem where we were told that the compression ratio is 18. We were told at the beginning of the cycle the temperature is 300 Kelvin, the pressure is 0.1 megapascals, the cutoff ratio is 2, and we're working with air standard. Not cold air standard, but air standard. If there's a difference in that one word, dictates what equations you can use when analyzing the system. It's annoying, I know, so please read carefully. You do not want to, for example, fail an exam or fail an analysis because you did not read the word cold. So read very, very carefully. But the problem wanted us to determine the temperature and pressure for each state. So what did we do? Well, we were told the values of state point 1 of 0.1 temperature, pressure for each state, thermal efficiencies, and the mean effective pressure. Thermal efficiencies, we need to know the work and the heat input and the heat rejection. Mean effective pressure, we need to know the work of the cycle and the specific volumes. Well, start with part A. Let's get the temperature and pressure for each process. So we went to state point 1, we were told the temperature and pressure, and from that we'll be able to go to our air table and get the internal energy and the reduced volume. From that, we were able to find the values of state point 2 by using the volume ratio of VR2 over VR1 is equal to the ratio of V2 to V1. Simplify that, and we can able to find the reduced volume value. We will take that value, go back to our air table, and interpolate, which we didn't do here because it's a waste of time for explaining the lesson. And we got T2 and H2. If you do not remember how to interpolate, I posted, I think it was my second video on reading tables. I covered interpolation there. From that, we need to find the pressure at state point 2. So we did the ideal gas law equation, and we found P2 and, found P2. We'll be able to get H2 again from that table. Oh, I did write it down. I just didn't see it. I did write it down. Huzzah. All right. So state point 3. Well, we know the pressure at state point 3 because based off a diesel cycle, as you can see, it is constant pressure from 2 to 3. So do ideal gas law to get T3, and once we get T3, we can find H3 and VR3 based off, again, the air tables. So state point 4. Volume ratios, find VR4. From VR4, we're able to get all of the temperatures. We don't know what VR4 is, and we don't know what VR3 is, but we can put them into ratios of the compression ratio and the cutoff ratio. From those, we can find the temperature and the internal energy. And bam. And then ideal gas law again to find the pressure down here. So now we need to calculate the thermal efficiency. Well, it's air standard, not cold air standard, so we cannot use this equation. This is a no. So we have to do work of the cycle over Qn. Now, work of the cycle is the pressure of P2 times the change in volume from 2 to 3, plus the work done from 3 to 4, minus the work of the compression from 1 to 2. Now, we do not know the change in volume from 2 to 3. We can find it because we find it later, but it's a lot of extra work for something we don't need to do right now. So, but we do know that the relationship that all the heat in has to equal the heat out, whether that's in, or all the energy in has to equal the energy out, whether that's in heat rejection and work. So energy in is equal to the energy rejected plus the work performed. So the work performed is equal to the energy coming in minus the energy or the heat being rejected. So we can use that principle here, which is what we do, Q in minus Q out, Q23 minus Q41, because we can find the heat in 2,3, if you recall, from it being the change in enthalpies. And 41, it's isochloric, just use internal energies, because work is 0. Where am I? Here we go. And you just simply plug in your numbers, you get 57.8% efficient. Mean effective pressure, work of cycle divided by the change in the difference in pressure between state point 1 and state point 2. So state point 1, factor out, you get 1 minus 1 over R. And now we need to know the work of the cycle. Well, again, work of the cycle is Q in minus Q out. Well, we know from here that Q out is 199 minus, or Q in is 199 minus 930. Q in or Q out is 664 minus 214. Plug that in, you get 617 kilojoules per kilogram. Then from that, we need to know also, as you can see here, the volume. So we use ideal gas law to find the specific volume at state point 1. From that, we then can find the mean effective pressure. However, since everything is in different units, we have to do dimensional analysis, and we finally get a mean effective pressure of 0.76 megapascals. This problem is how you will analyze diesel cycles. In the next episode, we shall cover dual cycles, which is a combination of a diesel cycle and an Otto cycle. If you have any questions, please leave a comment below and I will answer it. Also, if you found this video useful, please like and subscribe. Thank you very much.